All right, everyone sees the screen now with the mouse and everything? Okay, so yeah, so an analog signal would be something that, like the signal coming from an electrode, where at each point in time you have a different voltage and the voltage goes up and down, and you can plot it and you see things like action potentials. All right, so in terms of what we're going to talk about today, that sort of signal would be something more like say, for example, that you have some sort of sensor that senses, or say, for example, that you wanted to have a light where you could turn the light on to different levels of intensity, or a laser that where you want to give a laser like a sinusoidal laser stimulation. That's something where you have to give an analog signal that looks like a sine wave to the laser in such a way so that it will turn, so that you can encode values, not just on or off. And so digital signals or discrete signals, though digital signals are things where it's either on or it's off. Okay, so the things with digital signals is digital signals are, there's a sense in which they are analog signals, and that it is still just a voltage varying as a function of time. But but the difference is that the systems that send them and interpret them just okay, good. I can't emit people from here. Okay. Those systems will assume that they're either going to be high or low. Okay, so I'll try something here. All right, so, okay, good. Can everyone see that? Okay, so the idea here is that if you have an analog signal, you have voltage and time, and then just some sort of thing, varies as a function of time, right? So a digital signal looks like this, where you have some sort of voltage that goes up, down, like that. So if you were to sample this digital signal from an analog input, you would still see a voltage waveform. But the way that it works typically is that there's some sort of defined threshold above which is defined. Okay, now my pen stopped working. Okay, Illustrator's crashing, sorry. Let's see. All right, anyway. It'll be a problem if Illustrator crashes because the whole thing was going to be an Illustrator. So let's see. Here. Anyway, so but the point is that you define values that are high and values that are low. Okay, so the first thing to recognize about that is that there are, generally speaking, two logic families. All right, and one of them uses what we 5-volt logic versus 3.3-volt logic. Okay, so the old-fashioned everything ran on 5 volts, and it's 5 volts is on and 0 volts is off, and then what happened is that when electronics, advanced and there started being low power consumption circuits, then they switched to using 3.3-volt logic. So what happens sometimes is that there's you get these incompatible situations where you have something that outputs 5 volts and you have something that inputs 3.3 volts. So typically it doesn't matter too much, because so the thing is that a 3.3-volt signal, so with a 5-volt signal, it's usually that if it's above something like 2.0 volts, then that's considered on. So a 3.3-volt signal will still be read as on by a 5-volt, like a 5-volt input. But the only situation you have to be careful of is when you have a 5-volt signal that is going to a 3.3-volt input, whether it could damage it. So that's just something you have to be aware of, and we'll talk about that in a minute. Okay, so let me just. Okay. Okay, so let me see a share. Okay. Okay. So does anyone have questions about what I just said?
Can you give an example of a 3 versus a 5? Just like
so yeah, let me see. Erase my brushes too. Okay. So, second here. So, all right, so let's make this all very concrete. So this was my thinking more, so that we will okay, so we're going to talk about setting up a very simple experiment and then increasingly adding things to it. Then we'll sort of run into problems. We'll talk about how we can solve those problems. Okay, so now because of the way this is set up, I can't see any of you. So you have to talk if you want me to hear you, because I realize I have to see my screen. Okay, so this is the basic idea, which is a very simple experiment. You have a mouse inside of a chamber, and you have a nose poke of some sort that detects the mouse's nose poking in the hole, and then gives you digital output. Okay, so the digital output, for example, would be, say, a 5-volt signal. So when the animal sticks its nose in there, this output goes to 5 volts. When it pulls its nose out, it goes to 0 volts. And so somehow you want that information in the computer, right? So you have to somehow get that information through this DAC, which is data acquisition, into your computer. Okay, so, all right, so the way that you do this is you run a wire from that. So here's 5 volts. So this is something that is, has happened to me. That, so for example, our Intan electrophysiology setup uses 3.3 volt digital inputs, and most older equipment uses 5 volt outputs. So, but in most cases, they're just compatible with each other. But the only thing, like I was saying, is you just have to be careful you don't damage it. Okay? So in this case, we have something where the digital signal is really giving you timing, right? It tells you when something occurs, and it tells you how long each event occurs for. Okay? So then let's say, but this is not a very realistic experiment because we need to know something about what the animal is doing, right? So so we want to put a camera on the animal. So cameras, internally have their own analog to digital conversion, and they put some sort of digital signal that goes into a computer. And here I've drawn it as 2 separate computers, and it might be 2 separate computers, might be the same computer, but even if it's the same computer, it's different software on the same computer. So these things are now desynchronized, or they're asynchronous. So how do you know? The times. You have timestamps of when the animal nose pokes, but you can't synchronize that to the video in a trivial way. And so the answer to that, ideally, is to have cameras to give you a TTL pulse. So TTL is transistor logic. That's the old-fashioned 5 volts logic pulse signal. And so what happens here is you try to use cameras that are actually scientific grade cameras and have a digital output, which outputs 5 volts, and then you can sample that. And so now your computer is going to have, separately, you're going to have your video file, and then you're going to have your timestamp file on the computer, which is going to have timestamps of when the behavioral events occur, and then also when the TTL pulses occur. And so the way that these things typically work is that you would have 1 pulse for each frame that the camera acquires. So that's in theory. And in practice, this is always a mess, because it's often the case the frames are dropped, meaning that the camera says it acquires 1,000 frames, and you look and there's only 995, and sort of issues like that, or sometimes there's extra TTL pulses. So one thing that I'd recommend is that if you're doing something where timing is really important, you can also have an LED which flashes on top, say, and put an LED outside the box that the camera also samples. And then you can sample the LED turning on and off through your data acquisition system. And then that would allow you to post-hoc synchronize these two, even if your primary method fails. So synchronization is it's a pain, and it's something you're gonna have to deal with a lot if you're doing these types of experiments. And it sounds very simple, but it can get complicated. So yeah.
It bugged. Were you saying that the light, the flash LED has a control of when, something that can help synchronization between your TTL signal and your nose poke signal? Is the light supposed to be on and off when each time the mouse nose pokes, or is that what you're saying?
So yeah, no, so you could, I wouldn't do it that way, but you could do it that way. But the idea is more that you have some sort of common, that the light flashes on and off. So the best way to do it, I think, is to have the light turn on and off for random periods of time, and then just sample when that light turns on and when it turns off. And then the idea is that even if you have 5 different systems, if you sample the LED from, so if you record it from the camera and then you sample it from all your different systems, then you can always go back and synchronize them. It's better if that wouldn't be your primary mode of synchronization, but it's better if you do something like that, because say, for example, sometimes what happens is, say your camera software crashes in the middle of an experiment and you have to restart the camera. So now you've got two files. And if all you're using is something like TTL pulses, then it can create problems, because you might not be able to align, say, like a file that was interrupted in the middle based on something like that. But then if you have an LED, then you can cross-correlate the LED video signal with the LED electrical signal that you've recorded here, and then you can actually realign those things. So that's an example of when having sort of secondary synchronization methods is helpful.
I have a question related to that. I don't know why should the LED signal be random? Like, say for instance, every 100 frames you have an LED pulse, and then that will give you an indication that one frame has been dropped within that interval.
So that's an excellent question. Yeah. Okay, I'll tell you why. So the answer is that right. So there are times when, so I used to use a system that has some sort of a system where you have your LED signal and it would just be like this, completely regular, like that. And then what happens is a lot of times, so say that you record, and then the idea is that you're supposed to start recording before and then stop recording after, and then, so say that this is your camera, and then this is your eFizz, which is like that, right? But then what happens is that the danger with something like this is that it's highly correlated with time-shifted versions of itself, by which I mean that it would be correlated with that, like that. So you can be like, oh yeah, look, they're correlated. And actually, if you have millions of pulses and so forth, you can actually have shifts where you're off by one. Or for example, if you have some sort of thing that crashes in the middle and you lose a certain number in the middle, and now you have to record, these and match them up with the rest. When you have events that are regular, then you don't know how many you're off by. So that's the reason why it's actually better to do it randomly. So if you have something that goes up for some random period, where you have that period T, and that period is random, then here and then something like that, where that's going to be different every time, and then that thing will be a unique signature of that part of the experiment.
Wait,
Okay.
but
Yeah,
Luke,
that makes
isn't that, wouldn't you just do twice the frequency of whatever frame you're doing? So you're sampling at Nyquist? Like, I don't understand why you would do random instead of just making sure that you have enough LED pulses to match it.
So the reason why, like I said, is that this methods like this are fail safes for when stuff fails, right? So what I should say is that the duration of this time has to be longer than the sampling rate of the camera. So these pulses might last, say, like 500 milliseconds with on average with a 30 hertz camera. But the key idea here is that if you just have a train of regular pulses, you don't know if you have some giant recording that has all trains of regular pulses, and then if you have some broken, damaged file that just has a train of regular pulses, you don't know where in that file those pulses came from.
Okay.
I feel like I'm not doing a very good job explaining
this lecture 6 months ago, because we had this exact problem. We had regular pulses, and the problem is we had dropped frames, and we weren't sure if we were aligning the 5th pulse with the first LED or the 6th one with, we didn't know if we were actually matching the time, because
I get that
dropped frames.
kind of logic. So like in undergrad, we were taught that to avoid this kind of scenario, you just make sure you sample above Nyquist. So why is it that you're not?
So that's a separate issue. So what I'm talking about is so yeah, if your system works perfectly, then yes, you do that. What I'm saying here is a situation where something goes wrong. So what often happens with frame dropping, for example, is that you record, say, 10 minutes of electrophysiology data, and then your video file is 9.5 minutes long. And what happened is that randomly interspersed throughout there's missing frames. right? So the idea is that, or maybe all the frames are missing at the end, or maybe there's just a chunk in the middle, right? But the problem is that if your TTL pulses are regular with each frame, as they should be, then you can't go back and match them because you don't know which frames are missing. Do you understand?
Yeah, I understand that part. I just don't understand why you have to do the random pulses instead of just making sure you have enough pulses. Because you should be able to reconstruct if you have a high enough frequency.
Okay, so what you're talking about is something different. Okay, so you're right. So when you talk about the high enough frequency, what you're saying is that this. So if you're doing say 30 hertz camera, then your pulses have to be at 15 hertz or less, right? So you're in this case you're vastly oversampling the pulse rate with the camera. So sampling and Nyquist theorem and all that's not the issue. But the issue here is that if you use regular pulses, then each second or each say 10-second block of the experiment is not uniquely labeled. Because when you have random pulses that are different, so you can look at a chunk of data and be like, oh yes, that is second 544 to 548. That's that chunk of data from the middle of the experiment. And you can't do that with regular pulses because regular pulses are regular throughout the entire experiment.
Okay.
Does that make sense?
Yeah.
So it's a method by which each part of your experiment is given a unique signature.
Okay.
We can talk about it later. I'm still not 100% sure that people are getting that, but that's okay. That's not really a fundamental thing. Right. So anyway, so we have methods of synchronization. Okay. So let's see. Let's move on to this next one, which is so say we want to do photometry. Wait a second. Actually, it's not working. Anyway. So Joe, do you get it or not? Actually, let's make sure that we all are sure before we move on.
Oh, I mean, I get that would work. It just seems like a lot of effort instead of, never mind. Yeah.
So that's the thing is all right. So what's a lot of effort is when you spend 3 months doing recordings and you go back to analyze the data and recognize that you can't synchronize the video with the electrophysiology. So that's a lot of effort. So this is what I'm telling you is that there's like what the textbooks say, and then there's real life what you actually have to do. And what I'm saying is that this is the kind of thing that this is a redundancy that you can use that can help save you when these things fail because they fail.
Okay.
Right. So I'm saying that what you're talking about is in a system that works perfectly, right? And then the problem is that that's not how this stuff is, unfortunately. And you can't. So what I'm saying is things like electrophysiology generally are, but things like video collection, drop frames are common, or like desynchronization of the TTL pulses with the frame acquisition. That sort of stuff is super common. So it's something you have to deal with because these cameras are not designed with that level of sort of rigor in mind. You know what I mean? So the cameras they use to film the Hiroshima explosions and stuff, those cameras were super precise. But I'm saying even when you buy scientific grade cameras, allegedly scientific grade, they're not that precise. And it's not just the camera, it's also the computer has to be fast enough and the frame grabber card and all that. So anyway. So let's see. Let's say we want to add something more to this experiment now. So now we want to add optogenetic stimulation. So we have a laser shooting into the animal's brain. So we want to control this laser somehow. So up until now, we just have digital inputs in our DAC system. So now we want to have some sort of digital output, which we could use to drive it. So the idea here is you have a digital output, and that drives the digital input. So every time this thing goes to 3.3 volts, then the laser turns on. Then every time it goes to 0 volts, then that thing turns on. Right. So let's see. So one thing about this though is that generally speaking, when you put a laser into an animal's brain, it's not really a completely binary thing. It's not like you want to be able to control how much light goes in, right? So, but in this case, we have a digital output. So how do we control how much light goes in? So, and the answer is, pretty straightforward. Is that if you give a short pulse, right, versus a long pulse, then more light obviously goes in here than here. And so with this type of method, you're really controlling by the duration of the pulse. So another common scenario would be, for example, you have a syringe pump that delivers liquid reward. And the way most of these commercial syringe pumps work is that they deliver reward at a certain rate. So a short pulse, a pulse that short will deliver reward for that long. This one will deliver reward for that long. So the amount of reward delivered on a trial is based on the duration of the pulse, not based on some sort of analog value. Okay, so another thing to be aware of is a method called pulse width modulation, which is a method of, in a sense, getting pseudo-analog values out of digital outputs, which is that, say you have a light, so a common thing would be like an LED, and you want the LED to be at something like, say, 20% intensity. What you do is you just have it so that there is 20%, and then that's 80%. And then the idea there is that you can take the duration of that and you can extend that all the way to 100%, which LED is fully on, or you can make it 0 and LED is fully on. So that's pulse width modulation, and this is what's referred to as the duty cycle. Okay, so for certain things, it's easier to use this method than it is to use analog controls. Because there's a lot of, for example, light sources for optogenetics, like LEDs, for example, being something where the relationship between the analog signal you give it and then the number of photons that come out is not always linear. Whereas in this case, it is linear, right? Because it's if you do this, then you're getting 20% of the light, right? That clear to everyone? Hopefully. Okay. So, all right, the pulse width modulation method to convey continuous values with digital pulses. So we're going pretty fast. We're not going to have a lab component. So I just want to make sure, any questions about this so far? All right. So another thing maybe I'll throw in about this is that, yes.
Can you give example time-wise of a short pulse and a long pulse, for example, in the context of reward? How, like, what are we talking about, like 1 millisecond to 5 milliseconds, or?
Well, yeah, exactly. So that's a good question. So it depends on what it is you're driving. So if it's something like a syringe pump, right, where you might want to give a 1 second pulse versus a 200 millisecond pulse, right, in order to deliver a certain amount of reward. Whereas if it's something like an optogenetic laser, then you want to give generally very short pulses. So so that can get slightly complicated. So I guess what I would say is, yeah.
I thought that we were talking about optogenetics, so.
Yeah, okay, but I guess I'm talking more generally, yes. So for optogenetics, so I would say it depends on, maybe the more general answer to what you're saying is that the frequency at which you do this depends more on how fast the thing that you're driving it is. Right, so if you have, for example, an LED, if you have an LED and you turn it on, or some sort of light source, it actually takes a certain amount of time to turn on, then it takes a certain amount of time to turn off. And so for LEDs, that rate is typically very fast, as in nanoseconds or microseconds, depending on the type. But if it's some slower LEDs might be, say if it takes 200 milliseconds or something, then you're going to have to match this frequency to the rate at which that thing turns on or off. That's one thing with optogenetics. For example, the second thing with optogenetics is it depends what the kinetics of the response of the opsin itself are. And we're actually going to have a whole lecture on that. But for example, if you look at something like channel rhodopsin, so channel rhodopsin, if you just give a single light pulse like that, the response to channel rhodopsin actually goes up and then decays down like that. And so the H134R mutant, which people typically use a channel rhodopsin 2, it was specifically designed to have a slower decay constant because that increases the amount of current that's injected for each light pulse. So there's options with different kinetics, whereas if you're using something like Halo or Arch, which are pumps, they essentially shut off immediately as soon as the light pulse turns off. So with channel rhodopsin, you could give, say, 100 hertz stimulation or something, and the cell can't tell it's 100 hertz because the opsin is open continuously. But if you use these sort of faster opsins, using something like pulse width modulation at those frequencies, then you could actually entrain the cell's activity to that frequency, which you don't want. We'll talk more about that when we get to optogenetics. Trying to cover. Yeah.
So with any type of input like laser stimulation or delivery of like a liquid reward, when is it necessary, or is it necessary to have some sort of sensor to ensure that you know exactly what was delivered? Because say that like in a pump, there could be some variability in its operation. So
Yeah.
Where would you put that, and when would you need it? And
Yeah, so that's a very good question, and it's a combination of the synchronization issue and the the synchronization issue and the question of you know, like, is your system actually working like it's supposed to? So for example, in a system like this, in a perfect world, you know exactly when the digital outputs occur. So you can say, well, so I don't need to record anything from the laser because I know that every time that thing is on, then the laser is actually running. But the problem is that, what if the laser is broken, right? So when I use laser diodes, for example, I actually have a measurement where I measure the amount of current flow through the laser diode from the electrophysiology setup. And then that way, if the laser turned off, or if the diode breaks or something, then you know that even though you gave the signal to the laser to turn on, it didn't actually turn on. That's one thing. And then the second thing is just from a convenience perspective, is that typically, say you're doing electrophysiology and then you have some certain number of channels, and they have their clock, but then the clock that gives the timestamps for when the event occurs is a different clock. And so actually recording when the laser occurs in your electrophysiology part of it, so they're saved in the same file, makes it easier to synchronize them. Or it's essentially, it's synchronized for you. So in general, it's a good idea if you can to sample. If you give a signal to something, it's a good idea to sample it somehow if you can. For certain things like a syringe pump, you know, it's maybe not worth it because it's not an easy thing to sample either. But even for a syringe pump, I would recommend, so typically the software you use for the acquisition of the data, which then records the data on disk, is different than the software that you use to deliver commands. So it's actually useful to take something like this, then actually connect it up here. So say, you know, this is where you're recording your eFIS, for example. And then this is the command. So it's actually useful to sample what you sent out to the laser. Make sense? Claire?
yeah,
Okay.
thank you.
All right, so let me see here. How do I, oops.
I also have a question before we move on.
Mm-hmm.
So obviously you want to be like as precise as possible, but like functionally, how much wiggle room do you have? Like how, before you act, like if you have a plus or minus start time of your laser of a couple of like nanoseconds, or your duration is a couple nanoseconds off, like does that change in a like measurable way the mouse's behavior? Or if you have like a microliter less liquid reward, like
So,
how much wiggle room, like how much of an uncertainty is like standard in these kind of experiments?
So you're asking the right questions. I'm trying to figure out how to delete that thing that I put there. Anyway, you're asking the right question. So the answer is, I think it's not that. The answer is that it's different for everything, and you have to know, and you have to figure out what the answer is. So a nanosecond for a laser is not going to matter when you're talking about something like channel rhodopsin, which has, you know, response on the order of you know, microseconds on and milliseconds off. But you know, what plus or minus 1 microliter for a mouse is actually a lot of liquid. So you know, I don't know, for our experiments with mice, we typically give, say, like 2.5 microliter rewards, maybe up to 5, whatever. So 1 plus or minus 1 microliter is actually a lot. So I think that's what you're asking is the right question, but the answer is you just have to sort of, you have to understand your experiment and understand the equipment well enough to know where those problems are going to occur. And unfortunately, there's no simple answer to that. Okay. Another thing about lasers, just so you should recognize. So there's, I can't remember if we're actually going to talk about lasers at some point. Maybe we are. Maybe I thought maybe I was going to talk about it, but I'll talk about it now anyway. So there's different types of lasers. There's diode pump solid state, and then there's laser diodes, and then there's LEDs. Okay. So LEDs and laser diodes are more sort of similar in that they're current-driven devices where you give it some sort of current, and if you, so with LED is if you, the amount of photons that come out is a linear function of the number of milliamps of current that flow through it. So you can take an LED and you can, and they're very reliable, so you can do things like a ramp up like that, and it'll be exactly that every time, or you can give different waveforms and so forth. Laser diodes, excuse me, are slightly more complicated, but they're still more LED-like. A DPSS laser, so these are only available in certain wavelengths. For DPSS lasers, you have a much broader range of wavelengths. But then the problem is that if you give a pulse like that, then the laser response will actually be some sort of thing that looks like that. What's interesting is that it'll look exactly like that every time. So it's not that it's noisy, it's that there's something about the physics of what goes on inside the laser that makes it so it has this response. So you can get feedback regulated lasers, which are really expensive, but the method that people typically use is that if you just give very brief pulses, that the response to a brief pulse will be very uniform, where the response to sort of a long pulse won't be. That's an example of something where you might use, digital control and pulse width modulation versus analog controls, where you're controlling a current driver that has a feedback thing that passes current through either of those two. That was just a lot what I just said. Someone must not have fully got that. Any questions? No? All right.
I'll ask a question. So for when you're exciting, you typically do not need to use a long pulse, but when you're inhibiting, a lot of people typically kind of keep constant illumination there. So do you have any thoughts on like trying to inhibit?
Yeah. So that's why, so the reason for that, and we're actually going to talk a lot more about this, but the reason why is it has to do with the impulse response function of the opsin. So channel opsin 2, like I was saying, is that if you give a single pulse, then its response actually goes like that, right? So individual pulses, so you're actually injecting current for a long time. So that decay is, I think the time constant for the H134R mutant something like 30 milliseconds, 28 milliseconds. So if you give pulses at, once every 10 milliseconds, then it's practically just continuous. Like I was saying, but if you have something like a pump instead of an opsin, then you are actually giving that sort of thing. So there are, for example, so that's why you have to give, for inhibition, something like arch, then you have to give continuous light. And also it's the case that typically you might want to inhibit a cell for 10 seconds straight, but you're not going to just stimulate a cell for 10 seconds straight. So the problem you run into with this is problems of heating and tissue damage. And also, like I was saying, that the long-term stability. So LEDs are very good for this, but laser diodes can be prone to overheating when you give long pulses. The DPSS lasers, like I said, have that variability. And so there's heating of the tissue, but then also heating of the light source. You have to make sure stuff's properly cool. There are now chloride channel opsins. For example, like the GT-ACRs. And then those will have some sort of response that's more like that. So they're more channel rhodopsin-like. So you can use less light to get the same effect. So we'll talk about this let's talk about that later, another day, because it's important stuff to talk about, but let's stick to the basics for now. All right, so here we're giving light pulses, we're stimulating the animal's brain. Okay, so now say we want to add photometry. So here we have got digital inputs, we got digital outputs. So now with photometry, now we have a photodiode in there, and then an amplifier and everything gives you an analog output. So now we have something where the number of photons that this thing collects, as a function of time is an analog output. It's not a digital signal. So now we need to sample that somehow over here with our data acquisition. So we have an analog input and then we sample it. And that's pretty straightforward. However, and so this is real, this happened to me recently. So for example, we have a photodiode from Newport, and it has a 9-volt battery inside, and it outputs a range of 0 to 7 volts. So our analog inputs on the Intan board are 0 to 3.3 volts. So there's actually 2 mismatches here. And so the first thing to talk about here is saturation. So the idea is that your instrument is only linear over a certain range of values. So if you there's a gain setting on this photodiode that you can adjust. And if you adjust it too high, then what happens is your photometry signals get to be above 7 volts. And then what happens is that they essentially hit a threshold. So that if you were to look at it, some sort of thing like this, and then you have some sort of signal that goes like that. But in actuality, it gets cut off there, then your signal actually looks like that. And so you're actually, it's wrong. So so that would be the level where it's say something like 7 volts, okay? So the first level of saturation you have to go to is the saturation of the amplifier circuitry itself, the analog circuitry inside the amplifier. So you have to adjust the gain so that it's in the correct range. Okay, and this is something that's important, you'll encounter a lot, setting things so they're in the correct range. And then we have another level of saturation here where 7 volts is obviously too high for this. That only goes to 3.3. So how do we solve that? Any thoughts? At all? No thoughts? Okay, so I mean, one thing we could imagine doing would be to try to set this thing up so that we can configure it so that it never goes above 3.3 volts. So I'd recommend against that for a couple of reasons. One is that we're not using the full range of the full output range of this, so our signal's not going to be as good. The other thing is that what often happens with things like this is that in a lot of situations, you can actually damage this analog input if you give it more than 3.3 volts. So, so what you want to do is you want to have some sort of system where you can change that. Okay. All right. So the simple way to do this, and this is quite simple, something that any of you should be able to do after Googling, is a voltage divider. Okay. So the way when I set this up in the lab, what we did is we just had a 3-to-1 voltage divider. So like I said, the photodiag is of 0 to 9, but it's really only linear over that range. So if the most it can give out is 9, then you want it to make sure that this doesn't go above 3.3. So what I did is just essentially, so this is just, these are resistors here, right? And then, let's give me a second. So that's just a resistor. And so the idea here is that from there to there, you're going to have 9 volts drop over that thing. And so 6 volts of it are going to drop there, and 3 volts are going to drop there. So here you're essentially dividing the signal by a factor of 3. So this is the simplest way to do something like this when you have incompatible voltages, where one is higher than the other. If you need to increase the voltage, then it gets slightly more complicated. Or if you need to adjust the level, then you start needing to use things like op amps. Questions about that?
I have a really basic question, and maybe I'll just have to go back and learn these circuit diagrams. But
yeah. If
the signal is coming from the diode and passing through, you said this is a resistor. It seems to be passing through only one resistor before it goes to the analog input.
Okay, yeah. So here's so remember I said that voltages. So this is why it's important to recognize. So voltages, it's a relative thing between 2 different points. And in this case, it's the voltage. So when we say this is 9 volts, that's 9 volts relative to, sorry, it's ground here, and that's 0 volts. So that span right there is 9 volts. Okay, so yeah, so so if you just pretend that's not there, right?
Okay.
And now you can see that there's 9 volts there, and then so you have twice as much resistance here. So so it's gonna drop to 6 volts here, or I'm sorry. So here it's gonna be 3 volts.
Oh, I see.
And so that drop there is gonna be 6, and that drop there is gonna be 3.
Oh, okay. I get it.
And so, but you're right that this depends on. So one thing is that to recognize here is we're just sort of drawing this thing as a black box, but if you actually look inside that thing, it has some sort of sensor which has its own impedance and goes to ground. So the idea is that typically most analog inputs have very high impedance. So this might be on the order of something like 1 mega ohm or something. So, and the reason why is because if this impedance were low, say that this were 1 kilo ohm, and then you attach that thing, then now it's actually going to change the function of this. So the idea is that you generally speaking, your analog inputs should be high impedance, high enough that they are considered a rounding error.
Okay.
that when you connect them to the circuit, that doesn't actually affect the voltages that are in there.
Okay, thanks.
Okay, I know that's a lot, but what I'm saying is that in practice you can usually ignore. You can ignore that. You can just ignore that thing and pretend it's not there. Just say what you're doing is you're just sampling the voltage at that point relative to ground. So here you've got 0 to 3 volts.
That makes sense. Thanks.
Sure. All right. So. Okay. So now I guess the next question is, so how do we know what the voltage here was when we're at the level of the computer? So, excuse me, I'm going to get water. Oh, now it's coronavirus. Weird thing giving Zoom lectures. At least I'm wearing pants. So, all right. So the next thing. So okay, yeah. So there we go. Yep, the 3-to-1 voltage divider, or 1 to 3, however you want to look at it. Okay. So now these things match, and you're not going to damage your analog input. So now we have an analog input. And then we have a 16-bit A to D converter. Okay, so once again, this is actually real. This is the Intel system uses 16-bit A to D converters. So the question is now, so what does your computer actually see? What actually happens? You know, what is actually happens inside the computer, right? And so okay, so the answer is that okay. So if you have a 16-bit A to D converter, then what happens is, oh, whatever. Let's do 8-bit. How about that? So that you have a voltage that goes in there, and then the A to D converter has its range, which in this case goes from 0 to 3.3. So values of 0 are going to be 0 volts is going to be given the number 0 in the computer. And 3.3 volts, since it's an 8-bit A to D converter in this example, it's going to be given a number in the computer that's going to be 2 to the 8th minus 1, which is, so because it's 8 bits. So in this case, that's 255. So what that means is that if you get, if you're looking at your data file and the number is 0 for that sample, that means the input was at 0 volts. If it's 255, it was at 3.3 volts, and then if it was at, I guess whatever, 128, then it would be 1.65 volts. So it's usually a linear range. Okay, so if you look in the computer, so the 8 bits, meaning that it's represented in binary. So, you know, if you have something like that where it's all ones, then that's the highest number you can get, which would be, in this case, 255. So I should say there's 256 different values that it can take. But instead of going from 1 to 256, it goes from 0 to 255. 0 indexing. All right, so, excuse me. So in this case, so how do we calculate, so if we get a number here, how do we calculate what the voltage was there? Anybody care to take a stab at that?
Wouldn't you just have to multiply the reported voltage by 3? Because you divided it by 3 to get into the analog input.
Yes, that's right. Okay, but so, all right, so say for example that you have, all right, so let's say all right, so say that your sample gives you a value of, I don't know, let's see, 5,138 or something, right? Okay, so what voltage does that correspond to? So the way that you figure that out is, excuse me, so, you figure out what the voltage is for what they call the least significant bit. So what that is essentially, so like I said, it goes, so in this case, we have 16-bit A to D converters. That goes to, I guess, from 0 to 65,535. So. Okay, so every sample is from 0 to 65,535. And so the idea here then is that if you know that the range of that thing is 3.3 volts, and you know that it can take 2 to the 16th possible values, then I don't know, call them LSBs or whatever, right? So then you can figure out what the voltage is per change of value, digital value in the computer. Right, so in this case, if you actually calculate that out, which I did in advance, so you get 50 microvolts per bit, basically. Okay, so if you get this 5,138, you basically multiply that number times 50 microvolts, and then that tells you what the voltage was at the input to the A to D converter, and then you multiply that times 3 for the voltage divider.
Luke?
Yes.
What is that value? The sample, is it the number of bits that I'm a bit lost. 5,138. What is that?
Yeah. So okay. So
is there an accumulation of bits over time? I'm a bit lost.
So all right. So if you actually look at your input signal, there's a voltage, and then there's going to be some sort of continuous thing like that over time, right? And then if you actually look in your computer on the hard drive at the file, what's going to happen is there's a number. It's an integer. You have an integer value at each time point like that. And I'm saying if you took that one right there and look at the actual number, it's 5,138. So if we know that, then the question is, was the voltage there? You see what I'm saying? Like, how do we map from the number that's in the file to the actual voltage that was in the system at that time?
So it's a value at a specific time. It's not an accumulated value at the end of the experiment.
Right, exactly. So if you were to actually look at this, so if you record this, if you were to actually look at it in the computer, you would get this sort of thing where you'd have this giant, matrix of like 5,138, 5,139, 6,124, all the way down. And you just get this long column of numbers or row of numbers. And I'm saying those numbers correspond to voltages at the sensor. But the correspondence is determined by the relationship between, that the sensor goes from 0 to 3.3 volts, and it maps that range 0 to 3.3 volts onto the numbers 0 to 65,535, which is because it's a 16-bit A to D converter. Are you sure? You got it? Okay.
I think I got it because I remember seeing matrices like that when I recorded, but a little refresher on what type of data we are supposed to get when we record wouldn't hurt, but that's just my.
So we're actually going to talk about this in the next lecture. So this lecture, the idea is it's going to be more about sort of what does the hardware do, right? And then the next one is going to be, okay, so you've done your experiment, now what's on your hard drive? Like what is actually in the computer and how do you load it and what does it mean? Right, but the key idea here I'm trying to get at is that what the hardware does is it transforms a voltage into a number. And I'm saying that it's not so nice for you where it says, oh look, this was 3.1 volts. It gives you a number like 5,138. And then you have to figure out what's going on. Okay, so let's see, so get to in a second why that's important. Sorry. I hope, actually, maybe I do have coronavirus. Okay, so the key thing here is that this is a 16-bit A to D converter. So it gives you very high resolution, right? So whereas if you have an 8-bit converter where 2 to the 8th minus 1 is 255. So let's see if you had 255. So here you have 65,000 different values that it can take. But an 8-bit A to D converter only gives you 255 values that it can take. So in that case, you actually would not be able to probably wouldn't be able to reconstruct the signal with with enough resolution that will be good, as good as you actually wanted it to be, right? So, so this has a much larger dynamic range, meaning the largest number and the smallest number it can encode is much different. But the key things are that you have to, come back to this, you have to use, set your hardware correctly so that the voltage that's going into the A to D converter matches, so that we have a signal that goes between approximately 0 and 3.3 volts. It can't go above 3.3 volts or else it gets cut off and we lose the signal. Or if we made it that went from 0 to 300 microvolts, right? If we scaled this thing like a 1 to 300 or whatever it is, and then we had a signal that was just 100 microvolts tall, then you run into this problem where if each bit is 50 microvolts, then you're going to get a signal that says 0, 1, 2, 1, 0, 1, 1, 2, right? So you're only going to have 3 levels that encode that range. So you have to scale the signals in hardware so they match this, and then you have to know exactly what's going on at the level of the A to D conversion. So should we take a break for a couple of minutes so I can stop coughing? All right, okay. Any questions or anything before? All right. Kelly, you look tormented. You're like,
No.
like why? What mistakes have I made? What mistakes have I made in life? You know, I can see you, right?
Yeah. Well, I'll try to look more pleasant from now on.
The other funny thing is like seeing everybody's apartment, right? Like, Dewey, your apartment looks really nice. You got all the lights.
Me?
No, I said Dewey's apartment looks really nice.
Oh, Dewey.
Elliot's got some art there above the bed. I've got like my children's guitars, ceiling fan.
I tried, you apparently can green screen, and I tried it last
yes.
night, but it made my face Starry Night instead of the background. I decided not to do that today for the lecture.
Let's see how this works, guys.
I actually want to say that I'm sitting in my car because alternate side parking is not suspended, so that's why my camera is off. But
all right, let's see. So, okay, maybe we can start again. I honestly didn't have that much more I wanted to talk about because I was originally going to do some sort of demo with an oscilloscope and all that sort of stuff, but you know, whatever. Not gonna happen. So
I meant to email everyone. I think we scheduled for 2 hour, and you had mentioned it about like how much credit. I think we were gonna have like hour 30 and then a 2 hour on the days we did demos. So I don't think we need to go like fill 2 hours.
No, I know. I don't think anybody complains when the class is too short. You know, so that's fine.
That was just a weird thing with the scheduling that.
I think that happens a lot. Is that
we meet 45 minutes today and 3 hours the next. So we just did two hours. Anyway.
Could you suggest some material that is, I mean, maybe you will do it later, but a little less old for especially you know, I mean, whenever we're going to be doing the optogenetics, all of the latest tools out there that are trying to solve all of our compatibility problem or bleaching problem or stuff like that, because I'm super lost with those. And
so I'm gonna give a talk on optogenetics. So there's gonna be just a talk later on just biophysics of, you know, indicators, fluorescent indicators, and optogenetic tools and so forth. I think that it's more important that you understand the fundamentals about how they work at the biophysical level than it is that I mean, because then you can read a review paper and you can learn about all the newest ones. But a lot of people's naive conception about how they work is overly simplistic. And I think that understanding, you know, for example, the fact that it takes channel rhodopsin that long to turn off from a single light pulse is something a lot of people don't realize. And so what that means is that we'll talk about low pass filtering and filter kernels and convolution, all that, but it's the same thing with GCAM. So what you see is not, it's not, what you see is not always what's going on. And then the current that's being injected now is the same as the laser going in. So I'm sure we can find reviews that talk about the newest stuff, but it's all variations on the same themes.
Okay.
I know you'll want to talk about optogenetics, right? I know that, but I think this is actually this kind of stuff is the kind of stuff that you'll actually encounter and you'll have to troubleshoot. It's the kind of stuff you actually need to know. So you know, this whole thing is for you guys, right? It's not for us. So any questions, please? Seriously, actually, any questions on the first part? I know I went over a lot.
Yeah, I think I might have missed something in the very beginning. And I tried to catch up, but I still can't figure it out. This idea of the TTLs and lining up these LEDs. So I get that the camera frame rates drop and you want to line them up. Are you lining them up to the LED that follows the nose poke?
No. So, okay, yeah. So that's a good question. So I guess what I was saying is,
like, what's the LED? What other LED is there?
Yeah, so that's why I was saying that a lot of times so what I've done in the past and what we actually need to do, and I need to talk to you, because in my lab, we don't actually do this right now. And so,
okay.
well, so I should say there's a couple ways that you can solve the synchronization problem, and cameras are the trickiest. So one way to do it is to send TTL pulses to the camera, the trigger to acquire a frame each time that a pulse is given to it. And that's actually how we're doing it right now. And then you essentially can, when the pulses are given, you have timestamps of that, and you can actually record the pulses in your electrophysiology software, and then the camera will acquire frames at that time. Or you can do it the other way, where you tell the camera to record, and then you record the TTL pulses to come out of the camera, right? So you can essentially trigger mode versus, just sort of self-timed acquisition mode. So the and the problem is, like I said, is so that there's sort of two problems with it actually, and one of them is frame dropping. So what I mean by frame dropping is that data is flowing into the camera at a certain speed, and then it has to make it onto your hard disk or your SSD, whatever, fast enough. And if the computer hiccups for whatever reason, and the buffer overruns, then a frame is dropped. So that's something that often happens. And another situation is that it I think has to do with compression. So a lot of times compression algorithms used for video, which are lossy, sometimes mess up the frames. And sometimes you lose frames and stuff that way. So it's like you can have something compressed with two different codecs. So codec is like the algorithm for compression, decompression codec, and then they'll have different numbers of frames. And it's because we're using tools that were not designed for scientific experiments. Video formats and cameras and all this stuff was designed for sort of consumer applications or security, whatever. So it doesn't have rigorous timing and everything like we want it to. So what I was saying with the LED is that a good way to do synchronization is to so you have your camera frame like that, and then you have your box in the middle, nose poke, right? And the idea here would just be you have a light over here that flashes, so the mouse can't see it, but the idea is your camera's shining down, and then you can see that light. And then you have whatever the thing, I don't know, pulse generator, right? And those pulses go to the LED, and they also go to your data acquisition system. So that way you know when those pulses occur. And then when you look at your video signal, you actually have your video, and you can actually have things where you can circle that, and then you'll actually get a thing like that. It tells you when it was on, but in this case, instead of time, you have frames. And so this tells you as a function at time. And by time, I mean that particular clock, the clock used by the primary data acquisition. And then you can synchronize these frames to the clock. And then you can say at millisecond 308, this frame was active. Okay, and what I'm saying is that this is helpful when things crash in the middle, or if you have to piece together multiple data sets, or just any time that it doesn't work exactly like it's supposed to. It's good to have two methods if you can. So having the first method being that you record the TTL pulses from the camera, and a secondary method is also helpful.
Okay, that's much clearer. Thank you.
It's one of those things where it sounds like it's not necessary, but just you wait, okay? All right, so let's go back to this. Okay, so where are we? So now we have analog inputs, and we talked about that. Okay. Now we're going to talk about analog outputs. Okay, so analog output, for example, would be that you want to, instead of just giving pulses of light, you want to give, say, a sinusoid or white noise stimulation or ramp or some sort of analog function. So in theory, you could do that with pulse width modulation and so forth, but in practice, you can actually just use an analog control. So all right, so let me see. Okay. So here's what we want to do now. So, and this is once again a real life example of something that I've had to deal with, is that having a laser where it takes an analog input in the range of 0 to 1 volts, right? And then we need to drive that somehow. So it is possible to have an analog output directly on your DAC board that goes to there, but there's that's a whole complicated question, how you want to do that. And when you generate waveforms that have to be fast, if the timing on everything is fast enough to keep up. So the way that we it's often easier to have some sort of dedicated function generator, which will drive this thing and then trigger it with a TTL pulse from your data acquisition board. So, and I guess what I'm saying is that even if all these things being separate is not necessarily by design. It's possible to build a system where everything is unified into a single system. But the problem is that you typically will buy some sort of thing for this, and you buy some sort of electrophysiology board, and you buy a camera, and these things are all separate and have to be connected together. So that's what I mean, is it's often just simpler to have so in my old lab, we had this one called the Pulse Pal. It was the first generation one. And the next generation ones are better, but the original first generation one had an 8-bit DAC, so an 8-bit D to A converter. So what you do is you hook it up to the USB port and you load your waveforms into this buffer from MATLAB or Python or whatever, and then you trigger it. You send a TTL pulse to trigger it. So one thing about triggering, I already mentioned triggering with the camera, and I think one important distinction is that when you send a pulse here to the laser, then a 2 millisecond pulse gives twice as much light as a 1 millisecond pulse. But in this case, a trigger is something where it just detects either the rising edge or the falling edge of a pulse, and then at that precise moment, it does something. So it's just a timing signal, and the duration of the pulse doesn't matter. All right, so and then when you trigger it, it essentially takes what's in that buffer, and then it generates voltages with an 8-bit DAC, and it gives an analog output to there. So the analog output range of this thing is from -10 volts to 10 volts. And here you have a situation where you have an analog input of 0 to 1 volts and an 8-bit DAC. So does anybody see where there's a potential problem here?
The output can go up to 10 volts, and you have a 0 to 1 volt input.
Mm-hmm. So you could damage it, right?
Yeah.
I mean, that would be one thing, yeah. That you could, I mean, if your laser's not, and it's frustrating and amazing how much expensive scientific hardware doesn't have any sort of safety circuitry built in, so that you can fry a $20,000 laser by putting in 1.5 volts into its input and so forth. And just trust me, it sucks. So among stuff you're using, for example, lasers that have high-speed inputs, so forth, can be sensitive, that they don't have any protection circuitry. If you use things like Arduinos, if you do the slightest thing outside their range, it burns out that pin permanently. So, other things like National Instruments hardware, for example, is very expensive, but is very robust in that regard. Like you can plug in some 60-volt thing backwards, like I've done, and it's just fine afterwards. So anyway, it's just something you have to be aware of. So that's one thing that you could, if this is an expensive laser, you have to think very carefully about this. You know, because there's also situations where, for example, say that you reboot this function generator or whatever. Sometimes when you reboot it, it transiently drops to -10 and then +10 before it goes back to 0 or something like that. And I've seen stuff like that happen. And so you have to think about all this stuff. So the other problem, so this actually happened to this guy, Brendan, who was a postdoc in my old lab, where I loaned him this thing and he was all angry because his experiment didn't work. And what he was trying to do was he was trying to give a sinusoidal laser stimulation to this animal. All right, and so let's talk about what he was trying to do and how he ran into trouble. So what he wanted to do was to, give a laser stimulation where this would be 0 volts, and I think he wanted something like 200 millivolts. Right, and he wanted to give some sort of sinusoid that looked like that. Okay, so remember that our output goes from -10 volts up to 10 volts, right? And they're putting that, and then he wants to map that onto, and he wants to use this thing and then make a signal from 0 to 200 millivolts. Okay, so let's think about this from this perspective again. So we have a 20-volt range. So let's think about, now we're doing it in the opposite direction of what we did before, the mapping from analog to digital. So here we have 20 volts, which is this analog space, mapping into, there's an 8-bit DAC, 8-bit D to A converter, right? So that means, so 8 bits means that it can take 2 to the 8 values, which is 256, okay? So here we have 20 volts divided by 256, these significant bits. And what is that? It's, let me see, give me a second here.
It's like roughly 0.1 volts, right? A little bit more. A little bit less.
It is, sorry, it's 78 millivolts. Is that right? like 78 millivolts. Okay, so what that means is that the resolution of this device is that it makes things that go up and down. So it's not actually, it's not actually generating a true analog signal. It's generating a digital signal that has a certain resolution, and that those steps there are 78 millivolts. Okay, so now this guy wants to generate a signal from 0 to 200 millivolts. He wants to get this nice smooth sinusoid to drive his laser, and what he actually gets is something that looks like this. And he just gets these weird pulses, and he's like, "Oh, it's broken." And so, of course, it's not broken, right? It's just that the mapping was not good. So you can look at this two ways. One is that it's a crappy piece of hardware, which is having an 8-bit DAC. If you think about that, that's really not very good. So the newer ones have 12-bit DACs, which is much better. So you can have 2 to the 12th values. So actually, let's think about that for a second. So 20 divided by 2 to the 12th. So there you have resolution of 4 millivolts. So 4 millivolts would be probably enough for most things. So the other way that you could approach this would be to use a voltage divider here, for example. So say that you just did like a 1 to 10 division, right? So you have 128 values between 0 and 10 volts. So even if you just did a 1 to 10 voltage division, then you'd have at least 128 values you could work with. Right, so this is an example of something where you have to be aware of what's going on. The actual experiment was screwed up because of this. Does this make sense? Someone have a question? I heard someone.
Luke, yeah. Why would you want to have a sinusoidal signal in your animal? Like, what is is it to mimic a LFP signal, or?
So my guess is what the reason was is that it probably had to do something with they were looking for probably some sort of resonance, by which I mean that. So there's different kinds of things you can give. So giving pulses for channel rhodopsin, you can do that, and that's kind of boring. That's what a lot of people do. I have to do that, but then you can do things like a chirp, for example, where you have some sort of thing where you start off with like a slow frequency thing that gets faster and faster, whatever like that, right? And so then the idea here is that this ramps up slowly in frequency. And if you imagine you had some sort of cell that, fires a little bit here and then fires a lot in this range and then doesn't fire much there. And you could say that that cell has, damn it, Illustrator crashed again. Sorry.
Because what type of phenomenon is that supposed to mimic?
So the sort of thing I think is supposed to mimic would be things like if you had, some type of neuron that has resonance at theta frequencies, and your pulse goes in around 8 hertz or something, then the cell starts firing more, starts firing in train to the, firing in train to the sinusoid, something like that. I mean, I think that's the kind of thing they were looking for. Okay, gotta open this again. Bear with me. So I think that's the kind of thing they were looking for. Another thing you can do is you can do things like white noise stimuli. So white noise stimulus is actually an example of something that's probably a better use of the sorts of analog inputs. So let me think what else we got. I mean, that's pretty much the end of this stuff I was going to talk about. I was going to talk about the next lecture about representations inside the computer. Debating whether we should start that or maybe we should just talk about the optogenetics things. It sounds like people are more interested in that. So,
I don't think it's that we are more interested. I think that it's more concrete for us to understand.
Sure. So, well, I mean, I guess what I'm saying is, when I'm about to say something that's sort of outside the scope of, the principles we're trying to get at here. Let me, let's see. So why would you want to give an analog stimulus, right? Why would you want to give something other than just pulses? So, all right, let's talk about optotagging. So why is optotagging difficult and complicated? So one reason why optotagging, so the optotagging being that you want to give light stimulation that would, some cells would fire and other cells won't, and then you're like, oh, okay, the cells that fired are channel rhodopsin positive, and that means that they're somatostatin interneurons or something, because I'm using a somatostatin cream mouse. So the problem is that it's not so simple as that. And so one of the reasons it's not that simple is that, so say for example, you have, say for example, you have a bunch of pyramidal cells that are all channel rhodopsin positive, and then you have like a PV cell. Okay, and you shine light on this, and then all these cells fire at the same time, and this cell's gonna fire at the same time. And then you're like, oh, okay, this cell's channel rhodopsin positive. Right, so this is, it's actually not a trivial thing to disentangle this. So the time delay, for monosynaptic connection is only a couple milliseconds, and channel rhodopsin typically causes a certain number of milliseconds to bring a cell to the firing threshold. So if you just do something like you give a pulse of light, so what people often do for optic tagging is they'll give a pulse of light that's 50 milliseconds long or something. You have a bunch of cells that are kind of like, oh, they fire like that, and then whatever. But you can't tell if that cell's postsynaptic because the resolution you have there is far longer than the monosynaptic delay, right? So so this is a problem. It's a problem in particular when you have excitatory cells that you're stimulating, especially if you're so solutions to this kind of problem. And I should say, by the way, that the more cells you stimulate, the more likely you are to run into this problem. So if you have like a 200 micron core fiber, 500 microns away from your electrode, and you're putting in like 2 milliwatts of light or something, so you're just like blasting this thing, then you're going to stimulate cells all over. And then there's going to be, it's not necessarily something as simple as this, but there's going to be all sorts of network level effects that will affect the neuron that you're studying, the neuron you're recording, and then you won't know if that cell's channel rhodopsin positive or not, because it fires more or fires less. So, advantages or good approaches to this are, one, for example, things that will localize the site of the light illumination much closer to the electrode tip, such as micro LEDs on there, or fibers that have been soaked in hydrofluoric acid to taper them to a very narrow taper. So you can get much less light in a smaller way, with the smaller area. But then the other approach, which is probably is also not entirely perfect, is to do white noise stimulation with reverse correlation. So this is a method that has been used a lot. It was developed by engineers, I think, for reverse engineering alien technology, presumably. But visual neuroscience people have used it a lot, so that they'll give a white noise stimulus on a screen and then record from cells in monkey V1, and then they'll look at the correlation between this somewhat random stimulus. So white noise has two properties, which is that it's white, which means that it contains all frequencies. Oh, it's because my thing is bigger than it was before. Okay. And then the second thing is it's uncorrelated with shifts of itself. So it's not periodic. So for this example, if you give like a periodic train of pulses, then you don't, so say for example that you give pulses that were 10 milliseconds apart, right? And then if you had a cell that fired with a 10 millisecond delay, then you would be like, oh, look, the cell is firing with a 0 millisecond delay because you were assigning it to the wrong pulse. So white noise is uncorrelated with itself, temporal shifts of itself. So the idea is you give some sort of white noise stimulus, and then you pass that in to the cells, and you do this many times, and then what you'll get is if you average, you'll get some sort of response curve like that from the cell of firing rate, and then you can actually correlate these things together and then figure out what the time lag is by calculating essentially the cross correlation function between the two. And then this is the best way to get a precise measurement of time lag. And so in this case, this is what you want to do because what's most important is you want to try to be able to resolve the monosynaptic time lag to see if you can distinguish channel rhodopsin positive presynaptic cells from channel rhodopsin negative postsynaptic cells. And even methods like this are actually not perfect, but they're pretty good. Okay, so that's a good example of the time when you want to give an analog channel rhodopsin stimulation to a cell. That's actually relevant. All right. You guys can ask about whatever you want. I'm realizing that maybe it's more useful for you if I just answer questions that you care about as opposed to the questions that I thought were really important. So, all right. Okay, so why don't we just stop for now? How about that? What do you think, Anita?
And I was just gonna say also, we were given kind of a hard time about just having like 75% of your grade as participation. Apparently we have to quantify participation. So does everybody have access to Canvas?
Yes.
That's how you guys signed up for the class, so I'm assuming you do. So they asked us to include a formative assessment, which just means it's like a survey, like, did you like this class? What did you learn? So we're gonna have one of those for, I'm gonna take attendance, but I'm also gonna post one of these formative assessments, and then the due date will be like, I don't know, a week from the class or something, just so that we can have, you know, a record that people were participating. And I think it's especially important now that we're sort of doing this distance thing, so that we sort of have a record that we can show the school, oh, you guys logged in, you participated, we have records of that.
All right, so next time, then we're going to talk about, so next time is a little bit more reading, and we're going to talk about the data, the formats in which the data is stored inside the computer, and how it's important that you actually learn to load them in and understand what's going on. Numerical precision, things like understanding how big is a file going to be from an experiment, you know, how do I have to configure my computer to, you know, so that I can handle that. And then we're going to talk about a little bit about time versus frequency domain and sampling and filters and convolution and stuff like that. Okay.
I have a question before
Yeah.
we end. It's more about Zoom, I guess, or the class. Can we have? Is there any way to make like a record of these these whiteboards you're showing us? I mean, I've just been taking screenshots, but is there
the whole lecture is getting recorded, so.
Oh, okay. I didn't know.
Yeah, I guess
Okay.
I could have theoretically saved them somehow, but.
If it's recorded, then that's fine. I didn't realize.
Yeah.
I was gonna say, do we know where it's, you know where it's recording to, and we can like post it in?
I'm not sure that I do actually. I think we'll figure it
I know
out.
it's in the cloud, so, but we'll try.
I think I might have put it on my local hard drive actually. So, but
Okay.
I guess we'll find out when we're done.
Yeah, and wherever they go, we'll make sure you guys can access them from the GitHub or Canvas.
Yeah, we'll figure something out. Okay. All right, bye everyone. See you Thursday. I was cloud recording.